I'm sorry about that. My computer ran out of memory right in the middle of that video, so the video stopped. But I've cleared up a little bit. Okay, let's pick it up where we left off. So we are looking at, okay, the distance. Can we get an equation for the distance from our point xy to that point 0,2? Well, maybe you remember the distance formula, the distance between 2 points. Might sound vaguely familiar to you. Ignore what's going on over here just for the moment. Look in there. The distance d equals big square root. We take the difference in the x coordinates squared plus the difference in the y coordinates squared. It's kind of like x1 minus x2 squared plus y1 minus y2 squared. And then the square root. It does come from Pythagorean theorem. So that is the distance between our 2 points. We can simplify that a little bit. D equals the square root of x squared plus, and I'll just keep that as y minus 2 squared. Okay, so that's what we're trying to optimize. In this case, minimize. But there's always a second equation, the constraint. So where does that come from? Well, that's simply the equation for the parabola. We know we're constrained to the points on this curve. We can only pick points on that curve that are closest here and nowhere else. So there's our constraint. We know that's got to be true between our x and y coordinates of y equals 4 minus x squared. So we got our constraint already. We didn't have to do anything for it. Okay, so what do we do next once we have our two equations? We use the constraint to create one variable out of what we're trying to optimize. And this one's perfect. It's already solved for y. So we can take 4 minus x squared and just put it right in. So substituting, d equals square root x squared plus 4 minus x squared minus 2, all quantity squared. And let's clean this up, right? 4 minus 2. We can say 2 minus x squared squared. And you know what? Let's go ahead and just multiply this out. Now that it's all x's, I think it's a good time to FOIL. And I'll just show you the fully simplified version right there. Okay, so FOILing 4 minus 4x squared plus x to the fourth, and then rearranging, combining like terms, we get this. D equals the square root of x to the fourth minus 3x squared plus 4. Okay, looking good. Here's something interesting and a big reason why I bring up this problem for us to do together, since you're going to be seeing it in the homework. You need to see this logic here first. So I've just copied that equation, d equals square root x to the fourth minus 3x squared plus 4. And I want us to notice something. I want us to notice that that square root does not actually help us find the value of x that will minimize the distance. You might be thinking, what? What's going on here? Okay. What are we trying to do? We're trying to find the value of x that minimizes the distance, right? Well, think about just what's inside that square root. If we want to minimize the distance, don't we just need to minimize what's inside here? To minimize d is simply to minimize what's inside the square root. If we can find the value of x that minimizes what's inside, it's that same value of x that minimizes d. To minimize d is to minimize simply what is in here. If you can find peace with that, then this problem gets a whole lot easier. We're simply going to find the x value that minimizes, and we're just going to call it by a new name, f of x equals x to the fourth minus 3x squared plus 4. Let's find the x value that minimizes this. That same x value minimizes d. Now, why do we want to go this extra step? What's the big deal? Because we're going to have to take a derivative in a second, and I'd much rather take the derivative of the polynomial without the square root than with. Hey, we could take this derivative, sure. All right, so maybe even taking the derivative of that is not such a big deal. But remember, we are going to have to set this equal to 0 and solve it. And I'd rather take that derivative and set equal to 0 and solve than this derivative. It's possible we could do it, but why not make the problem a little bit easier if we can? Okay, so push pause on that. We're going to come back to this function. We're getting a little bit ahead of ourselves. We need to find that interval of x, or that domain of x, you might say. All right. Let's think back to the drawing and to the constraint. Okay, so the drawing, keep in mind, in the drawing we've got the whole thing, but we're only looking at x values that are on the positive side. We're not considering negative x values because we know once we get the positive, we can just, find that other point really quick. I suppose we could include 0 itself in our search because there's a small chance actually the closest point is directly above. Maybe that's as close as we can get. So only considering positive x values and 0, what's the smallest that x could be? Well, 0, of course, right? If it's directly above. Now you see my answer, but what's the largest that x could be? You think, well, if we're ignoring all that, if we're only considering here, then x could go out to infinity, right? I mean, we can allow x to go bigger and bigger. There's a point on the parabola, that corresponds to any big value of x. There is no largest x value. Now you might say, well, come on. I mean, really, is it going to be down here? It won't, right? I mean, the closest x value is not going to be down below in the negative y values, but, that can be misleading sometimes. We don't want to make assumptions like that. That's getting into dangerous territory. So just think, okay, on this curve, the smallest x value on the curve is 0. What's the biggest x value on the curve? There's not one. So we're just going to go with infinity. Okay, so our interval is 0 to infinity. All right. Now you will have homework questions that have domains like this, and not just problems like these with the graphs, where you've got to come to terms with, maybe the biggest x value is infinity. And those are tough things to wrestle with. Okay, let's move forward. We've got our function we're trying to minimize. We've got our interval. Now it's time to find the absolute min. Take a derivative. All right. We'll set it equal to 0. We'll consider if it does not exist. Well, the answer here is again none. Okay, this one, well, let's see. Solving there, let's factor out 2x. Leaves behind 2x squared minus 3. Setting both of those to 0. I'm just going to show you my work here. All right, we get x equals 0. And from the other one, adding 3 divided by 2, square root, we get square root 3 over 2. Again, we can ignore the plus or minus because we're only looking at positive x values. Okay, So we got our two criticals, and actually this was one of the endpoints on the interval. So to finish this off, we'll plug in both of those critical numbers we found into f, the original f, which was back here. There's f right there, right the inside, what was inside that square root. So plugging in 0, well, we get the 4. And I invite you to confirm this, plugging in square root 3 over 2. I would just throw that whole thing right into a calculator, and it'll actually come out to a decent answer, 7 over 4. Then we need to check that other endpoint. So we checked the 0 already. The other endpoint is infinity. Now technically we should be taking a limit here. We shouldn't say plug in infinity, but it works well enough for us, right? If we plug in infinity, infinity to the fourth, minus 3 times infinity squared plus 4, well, the infinity to the fourth will overrun everything, and it'll work out to be positive infinity. So what are we trying to do? Okay, we've got our 3 y values. Here we're looking for the smallest distance. We're trying to minimize. There is the minimum of f of x, 7 over 4. Okay, well done. Now, what exactly was the question? We go back to the original problem. Find the points that are the closest. Okay, it was the x and y coordinates. So that's the minimum f of x, but it came from x equals root 3 over 2. So we know that's the x coordinate of that point. We can plug in here to the constraint to find the y coordinate. So 4 minus square root 3 over 2 squared, kind of nice. We square the square root. And you'll find that y coordinate is 5 over 2. Works out pretty well. And so that positive point that's the closest is square root 3 over 2, comma 5 over 2. And from our drawing, we also know that we can take the negative x coordinate and get that second point negative root 3 over 2, comma 5 over 2 as well. Okay, guys, good luck in the homework. Hey, these questions are going to take a long time. So take a breath, make a nice drawing, come up with, take your time with those equations, and have fun with it.